first part about control surveying is the horizontal control. So for definition, control surveying establishes precise horizontal and vertical relationship of a network of monuments or markers which serves as a coordinate basis for subordinate surveys. So it uses unique landmarks which serves as the coordinate basis for their surveying works. So these are examples which utilizes control surveys: plant site control, deformation monitoring, aerial, topographic, and mapping. So for horizontal control, there are 5 types of techniques which measures angles and distance in horizontal control. The first is just traversing. Traversing is a type of survey in which a number of connected survey lines form the framework, and direction and length of the survey lines are measured with the help of angle measuring instrument and tape or chain. Next is the triangulation. Triangulation is a surveying method that measures the angle in a triangular form by 3 survey control points. By using trigonometry and a measured side of the triangle, calculating another point of the triangle is possible, creating another side of triangle, which is then used to calculate another point, which results in a chain of triangles with known distance. Next is the trilateration. The distance in a triangle could be measured directly instead of calculating them from observed angle. Since length of the triangle is measured, is one of the more accurate ways of establishing horizontal control. The process of calculating positions with chains of triangle is then same for triangulation, and since angles are measured, if need be, to increase accuracy. So these are the triangulation terms used. Triangulation station, the vertices of a triangle in a triangular system, the baseline, one of the lines in a triangular system whose length is precisely measured and its direction determined, usually located at the beginning of the system. Then last is a check base. Check base is one of the lines, usually a regular interval, whose length is precisely measured and serves as check for length calculation. So these are the error in control survey. The first is the line error, next is the angular error. Line error is usually done because of error in measuring distance on site, and the angular error same as the calculation for the distance or the measured error for the angles. The most satisfactory method of checking the linear measurements consists in chaining each survey lines a second time, preferably in reverse direction, on different dates and by different parties.
Good day everyone, I'm Vincent of Apilado and I will continue the report on triangulation and triangulation systems. A triangulation system consists of a series of joined or overlapping triangles in which an occasional side is measured and remaining sides are calculated from angles measured at the vertices of the triangles. Triangulation surveying is the tracing and measurement of a series or network of triangles to determine distances and relative positions of points spread over an area by measuring the length of one side of each triangle and deducing its angles and length of over 2 sides by observation from this baseline. So the applications of triangulation surveying is establishing accurately located control points for plane and geodetic surveys of large areas, establishing accurately located control points in connection with aerial surveying, accurate location of engineering projects such as center lines, terminal points and shafts for long panels, and center lines and abutments for long span bridges. So the commonly used types of triangulation systems are chain of single triangles, chain of quadrilaterals, and chain of polygons. In chain of single triangles, this figure is used where a narrow strip of terrain is to be covered. This system is rapid and economical, however, does not show accuracy for primary work, and it is not possible to carry triangles through the figure by 2 independent roads. So moving on to the chain of quadrilaterals. This afford an excellent system since the various combinations of sides and angles can be used to compute the lengths of required sides and checks can be made frequently. The best quadrilateral square, a quadrilateral with both diagonals having no station at their intersection, is usually employed. This is best suited for hilly areas. And lastly, chain of polygons. When areas that are very wide in proportion to their lengths are to be surveyed, then pentagonal or hexagonal figures may be economical. This may or may not have a central station. So this is an example of chain of triangles. This is an example of chain of quadrilaterals. This is an example of chain polygons. So
once again, good morning everyone. I'll be reporting about the vertical control under the control surveys. So the main objective in vertical control survey is to establish a network of reference benchmark. The elevations of these benchmarks are determined usually with respect to mean sea level or preferred datum. There are 5 ways to determine the vertical control surveys. So first is a barometric leveling. So it is well suited for reconnaissance surveys where approximate elevations are required. In this method of leveling, atmospheric pressure at 2 different points is observed, based on which the vertical difference between 2 points is determined. So next is the trigonometric leveling. So the process of leveling in which the elevation of point or the difference between points is measured from the observed horizontal distances and vertical angles in the field. It is often used when transferring elevations from precise leveling circuits to selected triangulation stations. So next is the differential leveling. So it is best run over level or gently sloping terrain. So next is the GPS or the Global Positioning System, which controls surveys utilize high precision surveys grade global positioning receivers to establish horizontal and vertical values for remote location. GPS supports the accurate mapping and modeling of the physical world from mountains and rivers to streets and buildings to utilize lines and other resources. Lastly is the photogrammetric methods. So photogrammetry can be defined as the science of making reliable measurements using photographs or digital photo imagery to locate features on or above the surface of the Earth. So photogrammetry has evolved into a reliable substitution of a ground surveying activities when large area of mapping is necessary.
We are now moving on to the second part of today's presentation. But before we start, we'd like everyone to scan the code or click the link in the chat box. The notes provided will hopefully help us go through our report smoothly and help you guys stay on the same page as us. Thank you. Again, we'd like everyone to scan the code or click the link in the chat box. The notes provided will hopefully help us go through our report smoothly and help you guys stay on the same page as us. Thank you. Good day. We are the Group 1 presenters from Block A, and we will be continuing our report on the topic of control surveys. I'm Miguel Allera, and today I'll be discussing about triangulation systems. Triangulation systems consist of a network of connected triangles which adjoin or overlap each other, the vertices of which are marked points on the Earth's surface. Usually, the triangulation system can be arranged to form 2 or more simple independent figures. An independent figure is one that is connected to each adjacent figure by one common side. The figures are termed independent if only one side is fixed and the angles of each independent figure can be adjusted independently. In practice, not more than 7 stations should be included in an independent figure. Before we proceed with the presentation, we must remember the terms that will help us understand the topic. First term is baseline. It's one of the lines in a triangulation system whose length is precisely measured and its directions determined, usually located at the beginning of a system. Second, check base. One of the lines usually at regular intervals whose length is precisely measured and serves as a check for length calculations. There are different geometric figure arrangements used to form triangulation systems which can be used for a particular survey. 4 of the commonly used types include: Number 1. Chain of single and independent triangles. A chain of single triangles is the simplest form of triangulation system since it involves a minimum of angular measurements and calculations for the amount of area covered. This type of triangulation system does not provide the most accurate results. Chain of single triangles is usually employed in long and narrow service of low precision, such as for a valley or a narrow body of water. Although it is the least costly to run, this system should be used only when it is impossible to arrange a strong system as the other methods. It is important in the system that no small angles should be included. Second type of geometric figure arrangement is a chain of quadrilaterals formed with overlapping triangles. It is the most commonly used triangulation system. It's best adopted to long and narrow service where a high degree of precision is required. Each figure is composed of two pairs of overlapping triangles, which gives the maximum opportunity for the distribution of angular errors. Although it is the most expensive system to use, it still is desired because it gives the highest accuracy. In the quadrilateral, there are 8 independent angles to be measured and 4 geometric conditions which must be satisfied. The third geometric figure arrangement is a chain of polygons or central point figures. The triangulation system is composed of a group of triangles having with it a station which is at vertex common to all the triangles. It is used when horizontal control is to be extended over a wide area involving a large number of points, such as a large triangulation survey for a city. Lastly, we have the chain of polygons, each with an extra diagonal, which is not far from the chain of polygons or central point figures. The difference is that when skewed, central point figures can be strengthened by using an extra diagonal.
So now that we know a little bit about triangulation systems and their types, we proceed to adjustment of a chain of triangles. There are two methods of adjusting or correcting measured angles in a control survey, and these are station method and figure method. These methods should be executed consecutively in the same order. So first is the station method. This is a method of correcting measured or observed angles per station of a control survey. There are 5 steps to follow in executing a station method. The first step is to get the total of all the measured angles within a station. This will be the value of your actual total angle. The second step is to subtract the actual total angle from the theoretical total angle, which is 360 degrees. This will be the value of your error. The third step is to divide the error by the number of measured angles in a station. This will be the value of your correction per angle. The fourth step is to add the correction to each of the angles of the station. This will be the adjusted value of your angles. And lastly, you proceed to the next station and repeat the steps above. The second method is the figure method. There are 5 steps in executing a figure method. First is to get the total of the interior angles of a formed triangle. This will be your actual total angle. The next step is to subtract the actual total angle from the theoretical total angle, which is 180 degrees for a triangle. This is the value of your error. The third step is to divide the error by 3, which is the number of interior angles in a triangle. This will be the value of your correction. The fourth step is to add the correction to each of the angles formed by the triangle. This will be the adjusted value of your angle. And lastly, you proceed to the next figure and repeat the steps above. In order to better understand the concepts we have covered so far, we will have a sample problem. For the given chain of triangles shown in the accompanying figure and tabulation, perform the station and figure adjustment by approximate method. So here we have a figure as shown. We also have a given of angles A through R. And so to perform the station method, we follow the 5 steps we have talked about a while ago. So for station A, we have angles A, B, and C. So the first thing we have to do is to get the actual total angle. And we have 240 degrees, 21 minutes, and 0 seconds. plus 60 degrees, 29 minutes and 10 seconds, plus 59 degrees, 10 minutes and 5 seconds, which equates to 360 degrees, 0 minutes and 15 seconds. We can then use the actual total angle in order to calculate for our error. We have 360 degrees minus 360 degrees, 0 minutes and 15 seconds, which gives us negative 15 seconds. We can then compute for the correction by using negative 15 seconds divided by the number of angles, which is 3, since we have A, B, and C. And that gives us negative 5 seconds. We then add the negative 5 seconds to each of the angles within station A. And so we get 240 degrees, 20 minutes and 55 seconds for angle A, 60 degrees, 29 minutes and 5 seconds for angle B, and lastly 59 degrees and 10 minutes for angle C. We can then proceed to do all the 5 steps in stations B, C, D, E, and F, as you can see below. We then have a summary of station adjusted values. As you can see, these are the values that we have gained from the correction that we have done using the station method. With this table, we can then do the figure method. For the figure method, we also have 5 steps to follow. We can see in figure ABC that we have interior angles C, E, and F. We then have 59 degrees and 10 minutes plus 58 degrees, 25 minutes and 13 seconds plus 62 degrees, 25 minutes and 12 seconds, which then equates to 180 degrees and 25 seconds. We can then get our error with 180 degrees minus 180 degrees and 25 seconds, which leaves us with negative 25 seconds. We then divide this by 3 since we have 3 interior angles in a triangle, and we then get negative 8.33 seconds. We then add the negative 8.33 to each of the interior angles in figure ABC. So we get the values 59 degrees, 9 minutes, and 51.67 seconds for angle C, 58 degrees, 25 minutes, and 4.67 seconds for angle E, 62 degrees, 25 minutes, and 3.67 seconds for angle F. We then proceed to do the same 5 steps to figures ACD with the interior angles B, G, and M. Figure CDE with the interior angles H, L, and O. And lastly, figure DEF with the interior angles K, P, and R. We can then summarize all the figure adjusted values by using the following table. As you can see, not all of the angles are corrected from the station adjusted values. This is because not all of the angles that are shown below are interior angles in the figure.
And now, we proceed to the topic of the strength of figures. By definition, it is a figure which gives the least error in calculated length of the last line in the system due to the shape of triangles and computation of the figures. It is when we consider the factor when triangulation system is said to coincide with the desired degree since precision is important. And now, we are presented with the basic formula for finding the strength of figures, which is the strength of figure factor multiplied with the logarithmic differences corresponding to the distance angles. So now, in order to get the strength of figure factor, which is F, we have a formula of 3 over 2 multiplied with P minus 2 divided by L minus 1, which in P would pertain to the number of stations in the figure, and L would be the number of lines in the figure. The summation component represents the difference per second in the 6th place of logarithmic sign in the distance angles. Now, I know this may be a handful or a mouthful, but we will discuss it and understand it together. Now, we are presented with a problem in finding the figure of the component in which line BC is the common side. First, let us know the component F, or its strength of figure factor. From this figure, there are 4 numbers of stations and 6 lines shown. We then plot the variables in the given formula, which gives us a value of 3 over 5 or 0.6 in decimal point. It's easy, right? Now we go to the fun part in finding the differences per second of the given distance angles. We use logarithmic sign, and in order to find and know which line and triangle to use, we need to find the triangles which share the common side of the figure given. We chose triangles ABC and BCB, wherein we can see that they share line BC. Initially, we get the distance angles for each side of the triangle. Note that the distance angles are the angles opposite to the side mentioned. Then, we proceed to getting its deltas, in which we get the difference for their logarithmic signs. So first, we get the delta for AB, in which we just get the logarithmic sign with a difference of 1 second. So as we can see, the distance angle of AB is 26 degrees, and the difference for that, when we subtract by 1 second, we then get the value of 4.31692766 times 10 to the negative 6. And by definition, the one we are looking for is the difference per second in the 6th place of logarithmic sign. So that is why we negate the value of 10 to the negative 6 and get the value of 4.31692766. The same goes with getting the value of the delta BC, in which we get the value of 1.529741346, and we proceed to the main equation of delta AB squared plus delta AB multiplied with delta BC plus delta BC squared, in which we get the value of 27.5976. Now we proceed to the triangle DCB, in which we do the same thing. We first get the distance angles of each side of the triangle, wherein DC is 56 degrees and CB is 68 degrees. Getting the deltas for CB and DC, we have the values of 0.8506788985. Now you may ask, why is it 0.8506788985 and not 8.506? Now note that the initial answer for that is times 10 to the negative 7, and by definition, we only get the 6th place of logarithmic sign. So that is why it's 0.850678985. And then we proceed to getting the delta DC, which we have the value of 1.4201783115. Now we go back to the main formula, wherein the strength of figure would equal to F, which is the strength of figure factor multiplied to the summation of the deltas that we solved early on. Now we have a value of 18.56026 as the strength of figure factor, wherein they share BC as the common side of the figure. I hope you learned a thing or two in finding the strength of figures. Thank you.